So we've seen that Schrödinger's equation is hard to solve for a single hydrogen atom. How do we go about solving it for an infinite collection of atoms? Well, it turns out that in a periodic system, like a crystal, it's not too hard to do, and the way to do it is to use Bloch's theorem. So in a crystalline solid, so let's just draw down a square lattice in which the atoms uniformly repeat, let's say at some distance a. If I sit on an atom and I translate by a vector r, in this case along the x direction and of length a, I'll sit now on another lattice side. Another possibility would be to translate at 45 degrees by square root 2a, and this would be another lattice translation vector. And every time I make a translation in the lattice of this amount, I must see the same physical environment about me. Solid-state physics textbooks tell you how to make the best choice of the lattice vectors, translation vectors for a given symmetry of lattice, but clearly what must be true is that if I measure any property somewhere at a point r plus r is the lattice translation vector, it must be the same as that property at a point r. What about quantum mechanical quantities? Well, in quantum mechanics, the measurable quantity is given by the square of the wave function. I actually write the wave function down here as psi nk of r, and we'll see why in a minute. The n has to do with atomic states, the k will be a quantity we will introduce. And the statement there is that psi squared nk of r plus r must be equal to psi squared of r. So let's take the square root of this expression, remembering we really mean that we're multiplying something by its complex conjugate, and we have psi of r plus r equals, and I'm going to put here the square root of 1 times psi squared r. Now, why did I do that? Oh, sorry, psi of r. Why did I do that? Well, I did that because this could be plus or minus 1. When I square it, I would recover 1. There's a more general expression for the square root of 1, which is to write it as e to the I kx. And the reason is that e to the I kx times its complex conjugate, e to the minus I kx, is of course 1. Therefore, the most general form of a wave function in a crystal is given by this expression you see here, that the wave function at some point r plus r is given by this phase factor e to the I k r times psi n k of r. This is Bloch's theorem, and this wave function is said to be in the form of a Bloch function. I've stated it two ways here. You'll see on the slide another statement in which we've used little r and a periodic function in r plus r. Now, let's write it down in the second form here. U of r, where this is a periodic function. And let's take a look at this quantity k. So let's take some displacement in a lattice that is the same everywhere you go in the lattice. K could vary all the way here, corresponding to k equals 0, since it doesn't vary with your position in the lattice, to the largest value, in which k, largest meaningful value, in which k switches sign. In other words, k is pi over a. This lattice spacing here is a. So now we have a factor e to the I pi and every possible phase in between. K then represents the phase of some displacement pattern or property as you move through the lattice, and it can go all the way from K equals 0, corresponding to a wavelength of an excitation in the crystal of infinity, up to a largest possible value, physically, in which the phase factor changed by 2 pi, the maximum possible in a cell, in which case lambda would be equal to A over 2. So, what does this mean? What it means is the effect of putting all these atoms together in a crystal can be done by solving the quantum mechanics purely for one unit cell of the crystal, and then putting in the displacement relative to the neighbors now as a function of a parameter k that varies between 0 and 2 pi over A. This range of phase factors is called the Brillouin zone, and the phase factor k is referred to as the crystal momentum. Now, because we can have waves that travel both in a plus k and a minus k direction, we can cover the range of 0 to 2 pi on A by taking k to be greater than minus pi on A and less than plus pi on A. And so now we will plot out quantities that for a single atom would have had just one value, one eigenstate. We'll now plot them out as a function of this crystal momentum k, and we will confine our calculations to a between minus pi on A and plus pi on A. Larger values of phase shift could be used, but they wouldn't mean anything because there are no atoms to displace at smaller distances than the lattice constant A.